What if I told you the universe isn't just a random scattering of galaxies drifting through empty space? That instead, every star, every spiral nebula, every colossal cluster is connected by an invisible scaffold, a hidden architecture so vast it defies comprehension. Picture this, a cosmic spiderweb stretching billions of light years across the void, its delicate filaments threading through the darkness, binding galaxies together in a dance older than time itself. This isn't science fiction, it's the cosmic web, the universe's best-kept secret, and the reason our night sky looks the way it does. For centuries, we've gazed up at the stars, mapping constellations, tracing the arcs of distant suns. But only now are we beginning to see the bigger picture, the breathtaking truth that galaxies aren't isolated islands. They're nodes in a grand design, held in place by threads of dark matter and gravity, woven into a lattice so fragile, so precise, it's as if the cosmos itself is embroidered with invisible silk. And here's the most astonishing part, this web isn't static. It pulses with energy, shaping the birth of new galaxies, guiding their movements, even determining their fate. So how does it work? Why does this hidden framework exist? And what does it mean for the future of everything? That's the mystery we're unraveling today. Because the cosmic web isn't just a curiosity, it's the blueprint of reality. It holds clues to dark energy's relentless push, to the way matter clusters in the void, even to the ultimate destiny of the universe. And the deeper we look, the more it feels like we're deciphering a love letter from the cosmos itself, one written in gravity, stitched with dark matter, and waiting, just waiting for us to read it. So let's begin, because this story isn't just about galaxies. It's about the fragile threads that connect us all to something far greater than we ever imagined. To understand the cosmic web, you have to think like a cosmic cartographer mapping the invisible. Those delicate filaments threading through space aren't just empty lines. They're rivers of dark matter, a mysterious substance that doesn't emit light but bends the very fabric of reality with its gravity. This hidden skeleton tugs galaxies into place, guiding them along these cosmic highways like beads on a string. And where these filaments intersect, that's where the universe gets crowded. Galaxies pile up into glittering megacities, bound together in massive clusters by the web's unbreakable grip. But here's the twist, most of this structure is made of stuff we can't even see. Dark matter makes up nearly 85% of the universe's mass, yet it's completely transparent. So how do we know it's there? The answer is written in the light of distant quasars, brilliant beacons shining from the early universe. As their light travels billions of years to reach us, it passes through the cosmic web's filaments, which absorb specific wavelengths like a fingerprint. It's as if the universe left us a shadow puppet show with dark matter casting silhouettes we can decode. Then there are the voids, the web's empty stretches, where galaxies are eerily scarce. These cosmic deserts can span hundreds of millions of light years, their vastness almost incomprehensible. Yet even here, the web's influence lingers. The emptiness isn't random, it's sculpted by the same forces that build the filaments, as if the universe breathes in and out, drawing matter into threads and leaving voids behind. What's truly mind-bending is how this web shapes destiny. Galaxies born along dense filaments grow faster, fed by a steady stream of gas, those near voids. They're starved, left to flicker in isolation. The cosmic web doesn't just connect galaxies, it decides their fate. And as we peer deeper into its structure, we're not just mapping the universe. We're reading its story, written in dark matter and starlight, one filament at a time. Dark matter doesn't just exist, it rules. Think of it as the universe's silent architect, sketching blueprints in gravity alone. While stars and galaxies glow brilliantly, they're merely decorations on a scaffold built by something we've never seen. This invisible substance doesn't just nudge celestial objects, it herds them, sculpting the cosmic web with the precision of a master weaver. Picture tossing glitter onto sticky threads. The glitter sparkles, but it's the hidden strands beneath that hold everything in place. That's dark matter's role, the unseen hand arranging galaxies into filaments, knots, and voids with mathematical elegance. But here's where it gets strange. Dark matter doesn't behave like anything we know. It doesn't collide, reflect, or emit light. It barely seems to notice the visible universe at all. Yet its gravity is so potent that entire galaxies orbit nothing, their stars whirling around empty space as if tugged by a ghost. Take the Bullet Cluster, where two galaxy clusters collided, and their visible gas crashed like cosmic traffic, but their dark matter sailed right through, unfazed. It's as if we're watching a play where most of the actors are invisible, their presence revealed only by the movements of the few we can see. Scientists hunt for dark matter like detectives piecing together a case with no fingerprints. Underground labs shield sensitive detectors from cosmic noise, waiting for the faintest tremor of a dark matter particle. Space telescopes map the web's gravitational fingerprints, tracing how it bends light like a lens. Even supercomputers simulate universes, tweaking the rules to see which version grows a cosmic web matching ours. Yet after decades, dark matter remains elusive, a shadow in the data, a whisper in the equations. Some theories suggest it's a sea of exotic particles. Others wonder if gravity itself works differently on cosmic scales. What's undeniable is dark matter's legacy. Without it, galaxies would spin apart, the cosmic web would unravel, and the night sky would be a lonely expanse. It's the reason we exist in a universe of structure, not chaos. And as we keep searching, we're not just chasing particles, we're decoding the hidden language of the cosmos, one gravitational clue at a time. Gravity is the silent choreographer of the cosmos, conducting the ballet of galaxies across an unimaginable stage. While dark matter provides the scaffolding, it's gravity that breathes life into the cosmic web, pulling matter into delicate filaments and dense knots over billions of years. Picture a river carving a canyon, except here, the river is gravity itself, and the canyon spans the entire universe. Einstein's revelation that massive objects warp spacetime wasn't just a breakthrough, it was the key to understanding how the cosmic web took shape. Every galaxy, every star, every speck of dust follows the curves in this invisible fabric, drawn together by the relentless tug of gravity's embrace. But gravity didn't work alone. In the early universe, tiny ripples in density, minuscule imperfections left over from the Big Bang became the seeds of everything we see today. Where matter was slightly denser, gravity had a stronger grip, pulling in gas and dark matter like a cosmic vacuum cleaner. Over eons, these patches grew into vast filaments, while the emptier regions stretched into voids. It's like watching a time lapse of ink swirling in water, except the water is space-time itself, and the ink is the very stuff of creation. Here's where the mystery deepens. If gravity were the only force at play, the cosmic web should have collapsed into a tangled mess long ago. Instead, we see gossamer thin filaments stretching millions of light years without breaking, while others knot into dense galaxy clusters. The answer lies in the universe's most enigmatic force, dark energy. As gravity pulls matter together, dark energy pushes space itself apart, creating a cosmic tug of war. In regions where gravity wins, galaxies cluster tightly. Where dark energy dominates, filaments remain stretched and fragile, like threads pulled taut. This delicate balance shapes everything. Without dark energy's repulsive push, the web would crumple. Without gravity's pull, it would dissolve into chaos. Together, they weave the universe's grand tapestry, one where every thread, every knot, tells the story of an epic struggle between attraction and expansion. And as we map this web, we're not just tracing the past, we're glimpsing the future, watching as gravity and dark energy continue their dance, sculpting the cosmos one filament at a time. Dark energy is the universe's silent rebel, an unseen force working against gravity's relentless pull. While gravity weaves galaxies together into the cosmic web, dark energy stretches the very fabric of space, pushing everything apart at an ever-increasing speed. Imagine holding a rubber band between your fingers, slowly pulling it taut. That's dark energy's effect on the cosmos, an invisible hand widening the gaps between galaxy clusters, thinning the web's filaments like strands of cosmic taffy. And here's the startling truth: this force isn't just present, it dominates, making up nearly 70% of the universe's total energy. But dark energy doesn't act alone. Its push is locked in an eternal struggle with gravity's pull, shaping the destiny of the cosmic web in real time. In regions where gravity wins, like the dense knots where galaxy clusters collide, matter clumps together in brilliant, chaotic cities of stars. Elsewhere, dark energy gains the upper hand, stretching filaments so thin they verge on vanishing, leaving behind vast, lonely voids where galaxies drift apart like ships losing sight of one another in an expanding ocean. The real question isn't just how dark energy behaves today, it's what happens next. Some theories suggest its influence could grow stronger over time, accelerating expansion until the cosmic web frays beyond recognition. Picture a tapestry slowly unraveling, its threads pulled so far apart that galaxies become isolated islands, their light stretched into oblivion. Other models propose dark energy might plateau or even weaken, allowing gravity to maintain some semblance of the web's structure. The answer lies in one of cosmology's greatest unsolved mysteries, the true nature of dark energy itself. Scientists trace its fingerprints in the afterglow of the Big Bang, in the way supernova dim as they race away from us, even in the subtle warping of spacetime around massive objects. Each clue hints at a force far stranger than anything Einstein predicted, one that might not just shape the universe's fate, but rewrite the rules of physics itself. And as we peer deeper into the cosmos, we're not just mapping the present, we're reading the first chapters of a story that ends with the universe itself, one where dark energy holds the pen. Galaxies don't drift alone in the cosmic ocean, they're strung along the universe's filaments like jewels on an endless necklace. Take our own Milky Way, nestled in the local group, a tiny neighborhood within the sprawling Laniakea supercluster. This supercluster isn't just a random gathering of galaxies, it's a single thread in the cosmic web, a filament stretching hundreds of millions of light years, with galaxies clinging to it like commuters on a celestial highway. And just as highways funnel traffic into bustling cities, these filaments channel rivers of gas into galaxies, feeding their star-forming factories and shaping their destinies. But why do some galaxies cluster shoulder to shoulder, while others hang in solitary splendor? The answer lies in the web's intricate architecture, where filaments cross, galaxies collide and merge, piling up into dazzling metropolises like the Virgo cluster, home to thousands of galaxies bound together in a gravitational embrace. Elsewhere, filaments stretch thin, leaving galaxies isolated in the voids, where star formation slows to a whisper and galaxies age in quiet solitude. It's a cosmic divide between the crowded urban centers and the rural outskirts of the universe, and it's all dictated by the web's invisible threads. The Milky Way's own story is written in this tapestry. Billions of years ago, it likely formed along a filament, drawing in gas and smaller galaxies like a cosmic magnet. Today, we're part of a local filament that's still feeding us, with gas streaming in from the intergalactic medium, ensuring new stars continue to ignite. But not all galaxies are so lucky. Those stranded in voids far from the web's nourishing currents slowly exhaust their fuel, their stars burning out one by one like embers in a dying fire. What's truly astonishing is how much the cosmic web resembles a living network. Galaxies aren't static, they migrate along filaments, drawn toward the densest knots by gravity's inexorable pull. In time, our local group will merge with others, drawn into the Great Attractor, a mysterious gravitational focal point pulling countless galaxies toward it. This isn't just structure, it's motion, evolution, a universe in flux, and as we map these threads, we're not just charting space, we're tracing the paths galaxies have traveled for billions of years and the journeys they have yet to begin. Between the dazzling threads of the cosmic web, there exists another world, one of profound emptiness. Cosmic voids stretch across the universe like silent caverns, some so vast they could swallow thousands of Milky Ways without a trace. These are not just gaps, they're active players in the cosmic drama, their emptiness sculpted by the same forces that weave the web's filaments. Picture a sponge. The dense clusters and filaments are its solid structure, while the voids are the pockets of nothingness that give it shape. Without these voids, the universe wouldn't just look different, it would be different. What makes these voids so fascinating is what they lack. While a typical galaxy cluster might pack thousands of galaxies into a few million light-years, a void might contain just a handful of isolated galaxies floating in a sea of darkness. The Boötes void, one of the largest ever discovered, spans 330 million light-years, yet hosts fewer than 60 galaxies. To put that in perspective, if our Milky Way were placed inside it, our nearest galactic neighbor would be so far away, its light would take tens of millions of years to reach us. It's the ultimate cosmic solitude, but emptiness isn't passive. Voids exert a gravitational influence all their own. As galaxies near the edges of these voids, they're tugged toward denser filaments like marbles rolling downhill. This motion leaves a fingerprint, a subtle redshift in the light of galaxies skirting the void's edge, betraying the invisible pull of absence. Even the gas within voids behaves strangely. Thin and diffuse, it's too sparse to collapse into stars, yet it carries echoes of the universe's infancy, undisturbed by the chaotic collisions that shape busier regions. Voids also serve as cosmic laboratories for dark energy. With so little matter to counteract its push, voids expand faster than the universe's average, stretching their boundaries over time. By measuring how voids grow, astronomers can track dark energy's grip on spacetime. Some theories even suggest voids could hold clues to alternate models of gravity, hints that Einstein's equations might need tweaking on the largest scales. Perhaps most haunting is what voids reveal about time. Light crossing a void travels unimpeded, offering a pristine view of the distant universe beyond. Peering through a void is like looking through a telescope with no atmospheric distortion, a crystal-clear window to the cosmic past. And as the universe ages, dark energy's dominion grows, meaning voids will stretch wider, galaxies will grow more isolated, and the web's threads will thin. In the far future, voids might dominate the cosmos, their emptiness a reminder of the universe's fleeting era of structure. For now, though, they remain silent witnesses to the cosmic web's grand design, a testament to the fact that even nothingness has a story to tell. To uncover the cosmic web's secrets, we rely on humanity's most advanced eyes in the sky telescopes so powerful they can trace the invisible. Take the Hubble Space Telescope, floating above Earth's distorting atmosphere. capturing galaxies so distant their light has traveled for billions of years. But Hubble's stunning images of spiral arms and star clusters are just the surface. By mapping the precise positions of millions of galaxies, Hubble reveals the Webb's grand architecture, how galaxies cluster along filaments like fireflies strung on wires. Then there's the Chandra X-ray Observatory, detecting scorching hot gas trapped in the Webb's threads, glowing faintly in X-rays. Where galaxies cluster, this gas reaches millions of degrees, heated by the gravitational squeeze of dark matter. Chandra's vision exposes the Webb's hidden energy, showing us the violent collisions and flows that shape its structure, but no single telescope can see the whole picture. The cosmic web reveals itself only when we combine observations across the electromagnetic spectrum. Infrared light pierces through dust clouds, uncovering galaxies hidden from optical telescopes. Radio waves trace cold hydrogen gas streaming along filaments, fueling star formation. Even the afterglow of the Big Bang, the cosmic microwave background, carries imprints of the Webb's gravity, subtly bending light from the early universe. It's like assembling a jigsaw puzzle where each piece comes from a different wavelength, slowly revealing the Webb's full majesty. The Sloan Digital Sky Survey revolutionized this work by automating the hunt. Using a telescope equipped with a 500-megapixel camera, it methodically scanned the sky, cataloging over 3 million galaxies and quasars. The result, a 3D map of the universe so vast it shows the Webb's filaments stretching across billions of light years, intersecting in dense knots where galaxy clusters collide. This map isn't static, it's a time-lapse of cosmic evolution, showing how the Webb grew from faint ripples after the Big Bang into the intricate scaffold we see today. Now the James Webb Space Telescope is taking the search deeper. With its infrared vision, Webb peers through cosmic dust to spot the Webb's faintest threads in the early universe, catching galaxies as they first lit up. Its observations could solve a lingering mystery: how the Webb's structure emerged so quickly after the Big Bang, defying expectations. Meanwhile, upcoming missions like ESA's Euclid and a Nancy Grace Roman Space Telescope will map dark matter's distribution with unprecedented precision, using gravitational lensing to trace the Webb's hidden skeleton. The challenge is monumental, like mapping a city's roads by studying the glow of streetlights from miles away. But with each new observatory, we refine our cosmic cartography, stitching together glimpses of the invisible. These telescopes don't just show us the universe as it is, they reveal the forces that shaped it, the threads that bind it, and the destiny that awaits it. And as our tools grow sharper, the cosmic web's grand design comes into focus, not as a static relic, but as a living, evolving masterpiece. To truly grasp the cosmic web's origins, we must turn to the digital universe where supercomputers breathe life into equations, spinning virtual cosmos from raw mathematics. These aren't just animations, they're time machines rewinding 13.8 billion years to replay the universe's birth, frame by frame. Take the Millennium simulation, one of the most ambitious cosmic reconstructions ever attempted. Using trillions of virtual particles to represent dark matter and gas, it revealed how microscopic ripples from the Big Bang fluctuations no larger than a quantum hiccup, stretched and amplified over eons, knitting themselves into the filaments and voids we see today. The precision is staggering. Run the simulation forward, and it spits out a universe that looks uncannily like our own, with galaxies clustering along delicate threads, mirroring telescope surveys down to the finest details. Yet for all their brilliance, these simulations aren't perfect replicas. Tiny discrepancies lurk at the edges, galaxies that spin too fast, filaments that appear slightly thinner than observed, voids that expand a fraction quicker than predicted. At first glance, these mismatches seem minor, but in cosmology, anomalies are gold mines. They hint at gaps in our understanding, whispering of physics we've yet to uncover. Could dark matter behave differently than we've modeled? Perhaps it's not a single, sluggish particle, but a family of interacting components, some tugging on visible matter in ways we haven't accounted for. Or maybe gravity itself weakens on cosmic scales, bending the rules Einstein set down over a century ago. Simulations let us test these wild ideas safely, tweaking variables to see which versions grow a cosmic web matching reality. The latest simulations, like Illustris TNG and UCHU, push boundaries further, folding in magnetohydrodynamics, black hole feedback, even the chemical enrichment of gas by generations of stars. They reveal how supermassive black holes at galactic hearts act like cosmic regulators, their violent outbursts heating surrounding gas and stifling star formation, effectively shaping the web's growth. Without these digital laboratories, we'd miss such subtle choreography, seeing only the universe's static snapshot rather than its dynamic story. But here's the humbling truth: no simulation can yet capture the full complexity of the cosmic web. The sheer scale of calculations tracking every particle across billions of years would require computers larger than galaxies themselves, so scientists cheat, using clever shortcuts and statistical approximations to mimic nature's chaos. It's like painting a masterpiece with only 10 brushstrokes. The broad strokes look right, but finer details blur. Yet with each leap in computing power, these virtual universes grow richer, sharper, more prophetic. Soon, exascale machines will simulate entire swaths of the cosmos at resolutions once deemed impossible, probing dark matter's quirks and dark energy's push with unprecedented fidelity. What's astonishing isn't just that these simulations work, it's that they teach us. By comparing digital universes to the real one, we're conducting the ultimate scientific experiment, testing our theories against the cosmos itself. Every mismatch is a clue, every success a confirmation that we're on the right path. And as these virtual realms grow ever more lifelike, they're not just mirrors of reality. They're windows into the universe's deepest secrets, waiting for us to peer through. Astronomers have long faced a cosmic accounting problem, a discrepancy so baffling it's called the missing baryon problem. Baryons, the building blocks of ordinary matter. Protons, neutrons, and electrons make up everything we see: stars, planets, even our own bodies. Yet when scientists tally up all the visible baryons in stars, galaxies, and gas clouds, they only account for half of what the Big Bang's afterglow tells us should exist. So where's the rest? The answer lies in the cosmic web's most elusive realm, the warm-hot intergalactic medium, or WIM, a ghostly haze of superheated gas threading through the universe's vast filaments. This missing matter isn't hiding in some distant corner. It's all around us, woven into the fabric of space itself. The WIM is so diffuse, so scorching hot, it barely interacts with light. Imagine searching for steam in a foggy room, except this steam is 1,000,000 degrees Celsius and stretches across billions of light years. Traditional telescopes see right through it, which is why the WIM remained invisible for decades. But astronomers have tricks to reveal its presence. When light from distant quasars passes through these filaments, specific wavelengths get absorbed, like a cosmic barcode revealing the WIM fingerprint. X-ray telescopes like Chandra and XMM Newton catch faint glows from the gas where filaments overlap, its heat betraying its location. Even the Sunyaev-Zeldovich effect, a subtle distortion in the cosmic microwave background, hints at the WIM energy as it scatters ancient photons. Yet these detections are like finding needles in a universe-sized haystack. The WIM density is staggeringly low, just a few atoms per cubic meter compared to Earth's atmosphere's trillions. But spread across the cosmic web's filaments, Those sparse atoms add up, potentially solving the missing baryon puzzle. Recent studies suggest the WIM could hold 30 to 50% of all ordinary matter, a reservoir vast enough to balance the universe's books. Why does this matter? Because the WIM isn't just hidden mass, it's a dynamic player in cosmic evolution. This gas acts as a bridge, funneling material between galaxies, feeding star formation, and even recycling the heavy elements forged in supernova. Without it, the cosmic web would be a static skeleton, not the living, breathing network we observe. And as the universe expands, dark energy's push may tear the WIM filaments apart, dispersing this matter so widely it becomes undetectable. The hunt for missing baryons is more than a census, it's a test of our cosmic models. If we can't find them, it might mean our understanding of the Big Bang's aftermath is flawed, or that baryons behave in ways we haven't yet imagined. Some theories propose exotic forms of diffuse matter, like dark baryons, hiding in plain sight. Others suggest the WIM could be clumpier than we think, with dense knots lurking undiscovered. Every new telescope brings us closer to answers. The upcoming Athena X-ray Observatory, with its unprecedented sensitivity, aims to map the WIM in detail, while radio telescopes like the Square Kilometre Array could trace its faintest ripples. Solving this mystery won't just fill a gap in our ledgers, it'll reveal how the cosmic web breathes, grows, and connects the universe's grand design. And when we finally account for every last atom, we'll have done more than find missing matter. We'll have uncovered a hidden chapter in the story of everything. Quasars are the universe's ultimate flashlights, beacons so luminous they outshine entire galaxies, piercing through the cosmic dark to reveal secrets hidden in plain sight. These brilliant objects, powered by supermassive black holes devouring matter at ferocious rates, don't just light up their surroundings, they cast shadows, etching the cosmic web's silhouette onto the fabric of space. Here's how it works. As a quasar's light journeys billions of years toward Earth, it passes through the web's delicate filaments of hydrogen gas. Each filament absorbs a tiny fraction of the light, leaving behind a unique fingerprint, a series of absorption lines known as the Lyman alpha forest. Think of it like holding a prism up to sunlight and seeing rainbows, except instead of colors, astronomers decode an intricate pattern of dark lines, each one a breadcrumb marking the presence of hydrogen along the quasar's path. This forest of lines is more than just a cosmic barcode, it's a treasure map. By analyzing its patterns across thousands of quasars, scientists reconstruct the web's three-dimensional architecture, tracing filaments too faint to see directly. Some filaments appear razor-thin, while others loom dense and massive, like cosmic rivers swollen with gas. The variations hint at a story written in the universe's infancy. During the first billion years after the Big Bang, gravity amplified microscopic ripples in matter, sculpting some regions into dense knots while leaving others stretched and sparse. Over time, these fluctuations grew into the web's uneven tapestry, with filaments inheriting their quirks from the primordial universe itself. Yet there's a puzzle. Some filaments contain far more gas than simulations predict. One theory suggests that black holes in early galaxies blasted winds of energy, shoving gas into nearby filaments like cosmic plows. Another posits that dark matter's peculiar behavior clumped ordinary matter more tightly in certain regions. Or perhaps the answer lies in forces we haven't yet discovered, an unseen hand shaping the web's threads in ways that defy current physics. Quasars don't just illuminate the present, they're time capsules. The light from the most distant quasars began its journey when the universe was a fraction of its current age, capturing snapshots of the web's youthful structure. By comparing these ancient beams with those from younger quasars, astronomers watch the web evolve, filaments growing thicker as gas funnels into galaxies, voids stretching wider under dark energy's push. It's like flipping through a photo album of the cosmos, watching eons pass in the shifting shadows of hydrogen. Every quasar studied adds another stitch to the cosmic quilt, helping us piece together how the universe weaves its grand design. And as telescopes grow sharper, probing fainter quasars and finer absorption lines, we're not just mapping the web, we're decoding the universe's diary, written in light and shadow, one brilliant beacon at a time. Gravity doesn't just move galaxies, it bends light itself, turning the cosmos into a giant funhouse mirror where distant objects appear stretched, warped, or even multiplied. This eerie phenomenon, gravitational lensing, is one of astronomy's most powerful tools for uncovering the cosmic web's hidden architecture. When light from a faraway galaxy travels through space, it doesn't move in a straight line. Instead, it curves around the web's massive filaments of dark matter, like a car winding through a mountain pass. The result, subtle distortions in the shapes of millions of galaxies, their images slightly smeared as if viewed through antique glass. Astronomers call this weak lensing, and it's the universe's way of whispering where dark matter lurks. But sometimes the universe shouts, in regions where the cosmic web's gravity is strongest, like the dense knots where galaxy clusters collide. Light bends so dramatically it creates celestial mirages. Distant galaxies stretch into glowing arcs, or even appear as multiple copies arranged in perfect rings around the lensing cluster. These Einstein rings aren't just stunning cosmic quirks, they're precision scales for weighing dark matter. By measuring how much the light bends, scientists calculate the mass of the invisible scaffolding responsible. One of the most famous examples, the Bullet Cluster, revealed dark matter's ghostly presence in breathtaking clarity. When two galaxy clusters collided, their visible gas crashed and heated, but their dark matter sailed through untouched, revealed only by how it twisted the light of galaxies behind it. The real magic lies in the numbers. Telescopes like the Hubble Space Telescope and the upcoming Vera-C Rubin Observatory analyze distortions in millions of galaxy shapes, stitching together a 3D map of the cosmic web's dark matter skeleton. The precision is staggering, like reconstructing a city's skyline by studying the shadows cast by its streetlights. Already, these maps have confirmed that filaments aren't just theoretical, they're tangible highways of mass, some spanning 500 million light-years. Yet mysteries remain. Some filaments appear denser than simulations predict, while others seem oddly sparse. Could dark matter interact with itself in ways we haven't accounted for? Or is gravity itself playing by different rules on cosmic scales? The next generation of telescopes aims to push these maps to unprecedented detail. The Euclid space mission, for instance, will measure lensing distortions across a third of the sky, probing the web's structure with pixel-perfect accuracy. Meanwhile, radio telescopes like the Square Kilometre Array will trace lensing effects in the faint glow of hydrogen gas, adding another layer to the map. With these tools, we're not just sketching the cosmic web's outline, we're filling in its textures, its knots, even its hidden fractures. And as the maps sharpen, they reveal something profound. The universe isn't just held together by gravity. It's sculpted by it, with every warped galaxy image a testament to the invisible threads weaving reality into shape. The cosmic microwave background is the universe's oldest photograph, a snapshot taken when everything was just 380,000 years old, a time so ancient stars hadn't even flickered to life yet. This faint glow bathing the cosmos in microwaves is more than a relic. It's a Rosetta Stone for decoding the cosmic web's birth. Hidden within its nearly uniform haze are tiny temperature fluctuations, minuscule variations, some as small as 1 part in 100,000. that tell the story of how emptiness and structure began. These imperfections weren't random. They were the seeds of destiny, the blueprints for everything that followed. Where matter was slightly denser, gravity had a foothold, pulling in gas and dark matter over billions of years until those faint ripples ballooned into the vast filaments and voids we see today. The Planck space mission transformed our understanding of these primordial whispers. With sensitivity so precise it could detect temperature differences equivalent to a snowflake's warmth in a blizzard, Planck mapped the CMB in unprecedented detail. What it revealed was astonishing, a pattern of hot and cold spots that align eerily with the cosmic web's modern structure. The hottest regions, they're the ancestors of today's densest galaxy clusters. The coldest patches, the embryos of the universe's most cavernous voids. It's as if the infant cosmos left us a trail of breadcrumbs, each one a clue to how dark matter's invisible scaffolding guided the growth of everything we see. But the CMB's secrets run deeper. Some of its fluctuations can't be explained by density variations alone. They hint at something more elusive: primordial gravitational waves, ripples in spacetime itself, forged during the universe's first trillionth of a second. If these waves exist, and experiments like BICEP and the upcoming Light Bird aim to find them, they could rewrite the cosmic web's origin story. Picture the early universe as a pond struck by a pebble. The waves from that impact would have jostled matter, potentially creating the initial density variations that gravity later amplified. Detecting them would offer a glimpse into an era before time, when the laws of physics as we know them didn't yet apply. The implications are staggering. If gravitational waves sculpted the cosmic web's first seeds, it would mean the universe's largest structures were born from quantum chaos, their fate sealed in the first instant of existence. Future observatories like NASA's Pico concept or the ground-based Simons Observatory are designed to hunt for these whispers. Their success could reveal whether the cosmic web is purely a product of gravity's slow dance, or if its roots stretch back to something far stranger, something that defies even our boldest theories. For now, the CMB remains our most direct link to the universe's infancy. Every time we map its subtle variations, we're not just studying radiation. We're reading the cosmic web's first diary entry, scribbled in heat and light when everything was just beginning. And as technology peels back more layers, we edge closer to answering the ultimate question: did the web's threads always exist, woven into the fabric of reality? Or were they spun by forces we've yet to imagine? The universe wasn't always a tapestry of light. For hundreds of millions of years after the Big Bang, it was a formless sea of darkness, its hydrogen gas too cold and diffused to spark the first stars. Then, something extraordinary happened. Gravity's patient pull began gathering matter along the cosmic web's faintest threads, and in those dense knots, the first galaxies flickered to life. These weren't the majestic spirals we know today. They were tiny, fragile things, barely more than clusters of newborn stars huddled along the web's primordial filaments like beads on a string. And now, thanks to the James Webb Space Telescope, we're witnessing their birth firsthand. Webb's infrared eyes pierce through the dust and time, capturing light stretched by 13 billion years of cosmic expansion. What it reveals is astonishing. Infant galaxies, smaller than the Milky Way by a factor of 100, already aligned along delicate filaments that existed when the universe was just a toddler. Some are so young they're still actively forming their first stars, their glow tinged blue with the heat of nuclear fusion igniting for the very first time. Others appear red, shrouded in thick cocoons of gas galactic embryos waiting to emerge. But the real surprise isn't just that these galaxies exist, it's where they're clustered. They didn't form randomly. They followed the cosmic web's blueprint, gathering where dark matter's gravity had already laid the groundwork. This discovery shakes the foundations of galactic archaeology. For decades, theorists assumed the first galaxies formed in isolation, collapsing from lone clouds of gas. But Webb's data tells a different story, one where the cosmic web acted as a cosmic midwife, guiding gas into filaments and funneling it into dense pockets where stars could ignite. The implications are profound. If the web dictated where galaxies formed, then dark matter didn't just shape the universe's structure, it orchestrated its very first lights. Yet puzzles remain. Some early galaxies are brighter and more massive than models predict, as if they grew up too fast. Others appear oddly mature, their stars already old when the universe was barely 1 billion years old. Could these outliers be evidence of exotic physics, dark matter interactions we haven't accounted for, or even primordial black holes seeding early growth? Or do they simply mean our simulations of the early web are missing a key ingredient, like turbulent gas flows or violent stellar winds? Every new web observation adds another piece to the puzzle. Recently, astronomers spotted a filament from the cosmic dawn, a thread of gas linking 3 infant galaxies, just as theory predicted. It's the smoking gun, proof that the web's architecture was already shaping galaxy growth when the universe was less than 5% its current age. And as Webb peers deeper, it's not just showing us how galaxies formed. It's revealing why they formed where they did, unlocking the hidden rules that turned darkness into light. What's emerging is a cosmic origin story more intricate than we ever imagined. The first galaxies weren't accidents. They were inevitabilities born from the interplay of gravity, dark matter, and the web's delicate filaments. And as we trace their origins, we're not just studying the past. We're decoding the universe's operating manual written in starlight, dark matter, and the invisible threads that bind them together. Where the cosmic web's filaments twist and collide, something spectacular happens. Galaxy clusters ignite into existence, glowing megacities of stars bound together by gravity's unrelenting grip. These are the universe's largest structures, titanic gatherings of thousands of galaxies, swirling in a superheated soup of gas that burns at millions of degrees. Take the Coma Cluster, a monstrous congregation over 300 million light-years away, where galaxies move so fast they'd escape their own gravity, if not for the invisible hand of dark matter holding them together. X-ray telescopes reveal its secret, an atmosphere of scorching plasma, so dense it emits more energy than all the cluster's stars combined. This gas isn't just leftover debris, it's the cosmic web's signature, proof that filaments funneled matter here for billions of years, building a gravitational powerhouse. But not all clusters grow equally. Some, like Virgo, dominate their corner of the web with thousands of members. Others, like the sparse Hercules cluster, remain modest by comparison. The difference lies in their location. The web's architecture is uneven, with filaments varying in thickness and density like branches on a tree. Where multiple thick filaments intersect, clusters feast on a constant flow of gas and galaxies growing fat with time. Isolated junctions fed by only a thread or two starve. It's a cosmic buffet, and the web decides who gets a seat at the table. The most fascinating clusters aren't the serene ones. They're the battlegrounds, places like the Bullet Cluster, where 2 galaxy clusters collided in a slow-motion wreck. The visible gas crashed and heated, but the dark matter passed through unscathed, leaving a ghostly fingerprint of its presence. These collisions are more than spectacular light shows, they're forensic evidence. By studying how clusters merge, astronomers weigh dark matter directly, proving it's not just an idea, it's the web's hidden scaffolding, the reason these galactic metropolises don't fly apart. Yet clusters aren't in points, They're way stations in an even grander journey. The web's gravity constantly tugs them toward one another, drawing them into supercluster structures so vast they make clusters look like neighborhoods. Our Milky Way, for instance, is part of the Laniakea supercluster, a sprawling network of 100,000 galaxies all sliding toward the same gravitational pit, the Great Attractor, a mysterious region of space pulling everything in its reach. This motion isn't random. It's the web's grand choreography written in galaxies and dark matter playing out over cosmic time. What's truly humbling is how much we still don't know. Some clusters host galaxies that age too quickly, their stars burning out far sooner than models predict. Others glow with puzzling X-ray emissions, hinting at exotic physics in their cores. Even the gas between galaxies behaves unexpectedly, sometimes clumping where it should be smooth, or vanishing where it should be abundant. Each anomaly is a clue, a whisper that the cosmic web's rules might be more complex than we've imagined. As telescopes grow sharper, they reveal clusters not as static monuments, but as living, evolving hubs, places where gas cools and ignites new stars, where black holes erupt with energy, where galaxies are torn apart and reborn. They're the universe's great laboratories, testing our theories of dark matter, dark energy, and gravity itself. And every time we study one, we're not just observing a structure. We're witnessing the cosmic web at work, weaving matter into meaning, one collision at a time. Threaded between the dark matter scaffolding of the cosmic web flows an electrified river of gas, a superheated plasma so energetic it glows faintly in X-rays, yet so diffuse you could fly a spaceship through it without noticing. This isn't just any gas, it's the universe's lifeblood, a primordial broth of hydrogen and helium left over from the Big Bang, ionized to millions of degrees and stretched into filaments that stretch between galaxies like cosmic power lines. When astronomers first detected this gas through its telltale ultraviolet absorption shadowy dips in the light of distant quasars, they were stunned. How could something so thin be so blisteringly hot? And why hasn't it cooled over billions of years to collapse into new stars? The answer lies in a cosmic balancing act more delicate than we ever imagined. The gas in these filaments isn't sitting still. It's constantly stirred by shockwaves from colliding galaxy clusters, supernova explosions, and the gravitational tug of war between dark matter and dark energy. Like water churned by 1,000 invisible paddles, it never gets a chance to settle. But turbulence alone can't explain the temperatures. Enter magnetic fields, invisible threads woven through the plasma, trapping particles in a frenetic dance. These fields act like cosmic insulation, preventing the gas from radiating away its heat too quickly. Then there are cosmic rays, high-energy particles racing through the filaments at near light speed, crashing into gas atoms and transferring energy like bumper cars in a particle accelerator. Together, they keep the filaments simmering at temperatures that defy intuition. Yet the real mystery isn't just how the gas stays hot, it's how galaxies manage to steal any of it at all. Against these furious energies, gravity must work overtime to pull gas into galaxies where it can cool and form stars. Recent simulations reveal a fascinating twist. Where filaments intersect, the gas piles up just enough for gravity to gain a foothold. Turbulence creates tiny density fluctuations, and like a surfer catching the perfect wave, galaxies positioned along these cosmic currents can siphon off gas despite the heat. The process is messy. Gas doesn't flow smoothly, it spurts in clumps and streams, some of it heated further by black hole outbursts as it falls inward. What's emerging is a picture of the cosmic web as both furnace and feeder. The same forces that keep the gas too hot to collapse also ensure it doesn't vanish entirely, maintaining a reservoir that galaxies can tap into over billions of years. Without this delicate equilibrium, the universe's star-forming factories would have shut down long ago. And as telescopes like Athena and the Square Kilometre Array come online, they'll trace these filamentary currents in unprecedented detail, revealing how the universe's largest structures keep its smallest lights burning. The cosmic web wasn't born intricate, it began as a whisper. In the universe's first moments, quantum fluctuations no larger than a proton stretched across the newborn cosmos, imprinting it with faint ripples of density. These microscopic wrinkles were the seeds of everything, the first filaments, the first voids, the first glimmers of structure in a formless sea of hot plasma. Gravity played the long game, patiently amplifying these ripples over hundreds of millions of years. Where matter was slightly denser, it pulled in more gas and dark matter, growing like a snowball rolling downhill. Elsewhere, regions emptied out, becoming the cosmic voids we see today. The early web was a ghostly sketch, its filaments wispy and faint, barely holding together the first protogalaxies. Then came the era of collisions. As the universe expanded, filaments crossed paths, merging into thicker strands. Galaxy clusters, drawn together by gravity, smashed in spectacular slow-motion crashes, their gas heating to millions of degrees and glowing in X-rays. These mergers didn't just build bigger structures, they reshaped the web itself. Shockwaves rippled through filaments, stirring the gas within and triggering bursts of star formation. Dark matter, indifferent to the chaos, flowed through the violence untouched, weaving an invisible skeleton that guided the visible universe's growth. Simulations like Illustris TNG replay this drama in stunning detail, showing how today's web emerged not from a single event, but from countless interactions over eons, each collision leaving its mark like brushstrokes on a cosmic canvas. Yet the web's story isn't finished. Dark energy, the mysterious force accelerating the universe's expansion, is rewriting the rules. As space stretches faster, filaments grow longer and thinner, their gas stretched like taffy. Voids, already vast, are swelling faster than the universe's average rate, their emptiness pulling at the web's threads. In the far future, galaxies bound by gravity will cling together, but those on the outskirts may find themselves stranded, their filamentary connections severed by the relentless expansion. The Virgo supercluster, our galactic neighborhood, will collapse into a single massive cluster while the rest of the cosmos recedes into darkness. This isn't just theoretical. Astronomers already see hints of the web's fraying edges. Distant quasars, their light absorbed by gas in filaments, reveal these structures were denser in the past. The WIM, the warm, hot intergalactic medium, is becoming harder to detect as it disperses. Even galaxy clusters, the web's strongest knots, show signs of slowing growth, their gas supplies dwindling as dark energy dominates. The cosmic web, once a bustling network, may one day resemble a tattered net, its strands stretched so thin that light from distant galaxies can no longer reach us. But here's the twist, the web's fate isn't uniform. In regions where gravity's grip is strongest, like the Laniakea supercluster, filaments may hold firm for trillions of years, nurturing galaxies long after the rest of the universe fades to black. These islands of structure could be the last bastions of light in an ever-darkening cosmos. Simulations suggest that while the web's grand architecture will fade, its legacy will linger in the motions of galaxies, their paths forever shaped by the filaments that once bound them. What's humbling is the scale of time involved. The web took billions of years to grow, and its unraveling will span even longer. We're witnessing just a snapshot, a fleeting moment when the web is at its richest, its filaments vibrant with gas and galaxies. Future astronomers, if any exist, might gaze into a sky where the Milky Way and Andromeda are the only galaxies visible. their light no longer competing with a backdrop of countless stars. The cosmic web story is a reminder that the universe isn't static. It's a living, evolving entity, its structure a temporary masterpiece in an endless dance of creation and dissolution. And as we map its filaments today, we're not just charting space, we're tracing time itself, from the first quantum ripples to the last fading threads of gravity's grand design. The universe is expanding, but not everyone agrees on how fast. This seemingly simple question has sparked one of cosmology's most heated debates, the Hubble tension. On one side, measurements from nearby galaxies and supernova suggest a relatively quick expansion rate. On the other, the cosmic microwave background, the afterglow of the Big Bang, points to a slower pace. The discrepancy isn't small. It's enough to make scientists wonder if we're missing something fundamental about the cosmos. And here's where the cosmic web enters the spotlight. What if this vast, invisible architecture isn't just a passive scaffold but an active player, subtly distorting our measurements? One compelling idea centers on cosmic voids, those sprawling, nearly empty regions between filaments. If our Milky Way happens to sit in one of these voids, the local universe around us might be expanding faster than average, like a bubble stretching in isolation. Meanwhile, the rest of the cosmos, weighed down by denser filaments, could be expanding more slowly. This would mean our local measurements of the Hubble constant aren't wrong. They're just skewed by our unusual cosmic address. Imagine trying to measure ocean currents while floating in a whirlpool. Your data would tell part of the story, but not the whole. But voids aren't the only suspects. The cosmic web's filaments themselves might be warping our view. These dense threads of dark matter and gas exert tremendous gravitational pull, bending light in ways that could trick our instruments. When astronomers observe distant supernova to calculate the universe's expansion, they assume light travels in straight lines. But if filaments curve that light like a funhouse mirror, our measurements could be subtly off. It's like trying to clock a race car's speed while looking through a lens that distorts the track. You might misjudge how fast it's really going. The implications are staggering. If the cosmic web is behind the Hubble tension, it means our universe's structure isn't just a consequence of cosmic laws. It's actively shaping how we perceive those laws. Resolving this mystery wouldn't just settle a scientific dispute. It could force us to rewrite textbooks on dark energy, gravity, and the universe's ultimate fate. Some theories even suggest exotic fixes, like dark energy that changes strength over time or undiscovered particles altering gravity's rules on cosmic scales. What's clear is this: the cosmic web isn't just the universe's skeleton. It might be its trickster, too, hiding clues in plain sight, nudging numbers just enough to keep us guessing. And as telescopes grow sharper, peering deeper into the web's filaments and voids, we're not just mapping space, we're deciphering a cosmic sleight of hand, one that could redefine everything we thought we knew. What if dark matter isn't the only explanation for the cosmic web's grip on the universe? A small but passionate group of scientists are exploring a radical idea: that we've misunderstood gravity itself. The theory, called modified Newtonian dynamics or MUND, suggests gravity doesn't fade as quickly over vast distances as Newton and Einstein predicted. Instead, it strengthens slightly at galactic scales, creating the illusion of invisible matter tugging on stars and galaxies. Picture a river flowing faster than expected. Instead of assuming hidden currents, maybe the water's viscosity changed. That's MUND gamble, rewriting physics to erase dark matter's need. The cosmic web becomes a proving ground for this bold claim. MUND proponents argue certain filament structures align better with modified gravity than dark matter halos. Some computer simulations even show man successfully forming cosmic web-like patterns without invoking invisible particles. The bullet cluster, often hailed as definitive dark matter evidence, faces alternative interpretations where gravity's tweaked rules explain the separation of visible and invisible mass. Yet for every success, man stumbles elsewhere. It struggles to replicate the web's precise large-scale structure or explain why galaxy clusters behave as if they contain 5 times more mass than we see. Enter darker horses theories like emergent gravity, where spacetime's structure generates extra gravitational effects akin to dark matter, or string theories, hidden dimensions leaking gravity in unexpected ways. These ideas flirt with elegance, suggesting the cosmos might not be filled with unseen particles but governed by deeper, undiscovered laws. The cosmic web's filaments, in this view, aren't threaded with dark matter. They're gravity's natural handwriting at cosmic scales. But evidence remains stubborn. The web's intricate details, like how gas clumps in filaments or how galaxies move within clusters, still match dark matter simulations more closely than any modified gravity model. Even when most ardent supporters concede it needs dark matter-like components to explain certain observations, muddying its appeal. The European Space Agency's Euclid telescope may soon settle the debate, mapping the web's growth with precision that could reveal whether gravity or dark matter better predicts its architecture. What's fascinating isn't just who's right, it's how the cosmic web forces us to question fundamental assumptions. Whether the answer lies in invisible particles or rewritten physics, the web's filaments hold up a mirror to our ignorance, revealing how much we still don't understand about the universe's hidden rules. And that's the beauty of science. Sometimes the most profound discoveries begin not with answers, but with the courage to ask. We've been asking the wrong questions all along. The next decade promises to rewrite our understanding of the cosmic web, not with incremental steps, but with quantum leaps in observation. The European Space Agency's Euclid spacecraft, now streaking through the void, is on a mission to map over 1 billion galaxies across 10 billion light-years, a survey so vast it will reveal the web's structure with razor-sharp precision. Unlike its predecessors, Euclid won't just catalog galaxies, it will trace the invisible. Using gravitational lensing, it'll measure how dark matter distorts the light of background galaxies, effectively weighing filaments down to their quantum quirks. Early test images already show staggering detail, threads of galaxies stretching across the cosmos like veins in a cosmic leaf, their curvature betraying the gravitational hand of unseen mass. Meanwhile, on a Chilean mountaintop, the Vera Rubin Observatory's 3200 megapixel camera is preparing to scan the entire southern sky every few nights. This isn't just mapping, it's time-lapse cosmology. By catching fleeting events like supernova and quasar flickers behind filaments, Rubin will measure how the web's gas absorbs light at different epochs, effectively creating a 3D movie of the web's evolution. One of its holy grails, spotting filamentary lensing, where entire threads of the web bend light subtly but detectably, proving their mass extends far beyond visible galaxies. But the real revolution might come from an entirely different angle: gravitational waves. Future observatories like LISA, a space-based detector sensitive to low-frequency ripples in spacetime, could catch echoes from the universe's first billion years, when filaments were just condensing from the primordial soup. Theorists predict these waves might carry imprints of the web's earliest vibrations, like sonar pings from the cosmos's infancy. If so, we could witness dark matter's first gravitational whispers as it began weaving the web. Back on Earth, the hunt turns microscopic. Deep in abandoned gold mines and under Antarctic ice, ultra-sensitive detectors lie in wait for dark matter particles to bump into atomic nuclei. Experiments like LUX Zeppelin and Xeno NNT have ruled out entire classes of hypothetical particles, narrowing the search. A confirmed detection wouldn't just solve the Webb's scaffolding mystery, it could reveal why filaments have the exact thickness and distribution we observe. Some models suggest certain dark matter types would clump differently, leaving distinct signatures in the Webb's architecture. The synergy between these approaches is where magic happens. Euclid's dark matter maps could guide physicists to the most promising particle theories, while lab discoveries might explain odd filament features in Rubin's data. Gravitational waves might timestamp when the Webb's first strands tightened, cross-checking supercomputer simulations of cosmic dawn. Together, they form a feedback loop, each discovery refining the others, peeling back layers of cosmic history. What's at stake isn't just academic. If dark matter interacts with itself even faintly, as some filament observations suggest, it could mean the Webb is subtly evolving in ways we've never accounted for. Or if Euclid finds voids expanding faster than predicted, dark energy's nature might be stranger than we thought. Every anomaly holds potential to upend cosmology, not with a shout, but with a whisper hidden in the data's quiet corners. We stand on the brink of a new era where the cosmic web transforms from a static map into a dynamic, evolving entity we can study across time and scale. The tools we're building today aren't just telescopes and detectors, they're time machines, particle colliders, and cosmic scales all in one. And as they switch on, we're not just observers anymore. We're participants in a grand unraveling, threading together the universe's deepest secrets one discovery at a time. Black holes aren't just cosmic vacuum cleaners, they're titanic sculptors, shaping the universe on scales so vast it defies imagination. At the heart of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, some weighing billions of times the Sun's mass. These gravitational monsters don't just sit quietly. They erupt, launching jets of plasma at near light speed that stretch for thousands of light years, injecting energy into the cosmic web's delicate filaments like a blowtorch to gossamer threads. The impact is staggering. When these jets plow through intergalactic gas, they heat it to millions of degrees, preventing it from cooling and collapsing into new galaxies. Picture a cosmic thermostat. Black holes switch on when gas flows too densely, their outbursts pushing back against gravity's pull, ensuring star formation doesn't run wild. In galaxy clusters like Perseus, Chandra X-ray observatory images reveal vast bubbles carved by black hole jets, their energy rippling through the surrounding gas like shockwaves in a pond. Without this feedback, theorists suggest galaxies would grow unchecked, devouring gas so quickly the cosmic web would look more like a tangled knot than an elegant lattice. Yet black holes might play an even deeper role. Some simulations show their eruptions don't just suppress growth, they channel it. By heating gas unevenly, they create pressure differences that funnel material along specific filaments, steering galaxies into dense knots where they collide and merge. It's as if black holes are cosmic traffic controllers, redirecting the flow of matter to build the web's most massive structures. The Phoenix cluster offers a stunning example. Its central black hole's outbursts are so powerful, they've created a feedback loop where gas cools, fuels the black hole, and triggers new jets in a cycle that shaped the cluster for billions of years. The most tantalizing idea, black holes could be the web's hidden architects. Their seeds, forged in the universe's first moments, might have acted as gravitational anchors, pulling dark matter and gas into early filaments that eventually grew into today's vast network. Observations of quasars, supermassive black holes shining brightly in the early cosmos, show they often sit at filament crossroads, as if they marked the web's foundational nodes. If confirmed, this would mean black holes didn't just grow within the cosmic web, they helped weave it, but mysteries linger. Why do some black holes, like M87s, unleash jets powerful enough to reshape entire clusters, while others, like Sagittarius, a star in our galaxy, remain relatively quiet? Could the differences hint at undiscovered physics governing how black holes interact with the web? Upcoming telescopes like the Square Kilometre Array aim to trace the faint radio whispers of ancient jets, mapping how black hole activity has shaped filaments across cosmic time. What's clear is this: black holes and the cosmic web are locked in a dance of creation and destruction. They don't just inhabit the universe, they engineer it, balancing chaos and order with a precision that feels almost deliberate. And as we uncover their secrets, we're not just studying celestial objects, we're decoding the invisible forces that spun the universe into being. Neutrinos are the universe's silent ghosts, particles so elusive they pass through entire planets without a whisper. Born in the cores of stars, supernova, and even the Big Bang itself, they flood the cosmos in unimaginable numbers, trillions streaming through your body every second. Yet for all their abundance, neutrinos barely interact with matter, making them nearly impossible to catch. But here's the twist: despite their ethereal nature, these tiny particles might hold enough collective gravity to subtly reshape the cosmic web itself. Imagine the web's filaments as rivers of dark matter and gas flowing under gravity's pull. Now picture neutrinos, each one almost weightless but trillions upon trillions strong, adding a faint gravitational push to the mix. Their combined influence isn't enough to build structures, but it could slow the growth of filaments, like a gentle breeze resisting a river's current. This might explain why some supercomputer simulations of the cosmic web don't quite match observations. When models account for neutrinos' tiny but pervasive mass, the simulated web's filaments appear slightly thinner, its voids marginally larger, closer to what telescopes actually see. The challenge is proving it. Neutrinos are so light that their gravitational fingerprint is vanishingly faint, buried in the noise of cosmic evolution. Yet astronomers are devising ingenious ways to spot their handiwork. One approach studies the universe's first galaxies. If neutrinos suppressed early structure growth, those galaxies should cluster differently than predicted. Another looks for subtle distortions in the cosmic microwave background, where neutrinos' gravity might have left a whisper-thin imprint. Even galaxy surveys, like those from the Vera Rubin Observatory, could reveal neutrino effects by mapping how filaments deviate from dark matter-only models. What's tantalizing is the scale of the puzzle. Neutrinos make up less than 1% of the universe's mass, yet their impact, however slight, could be the missing variable in our cosmic equations. Some theories suggest they might even interact with dark matter in ways we haven't imagined, adding another layer of complexity to the web's formation. It's a reminder that the universe's grand design isn't just shaped by the obvious players. Sometimes, the smallest actors leave the most intriguing clues. As detectors like Dune and Hypercamioc and hunt for neutrinos' properties with unprecedented precision, we're not just chasing particles. We're piecing together how the cosmic web's faintest threads were spun and rewriting the rules of structure itself. Because if something as ghostly as a neutrino can bend the universe's architecture, what other invisible forces might be hiding in the darkness? What if our cosmic web, with its delicate filaments and vast voids, is just one thread in an infinite tapestry of universes, each with its own version of structure? In the realm of multiverse theories, the rules of physics aren't set in stone. They're variables shifting from one universe to the next, and with them, the very fabric of reality twists into forms we can barely imagine. Picture a cosmos where gravity is stronger, yanking matter into thick, knotted filaments that leave no room for voids. or one where dark energy dominates so fiercely that galaxies never cluster, scattering like dust in an eternal wind. These aren't just thought experiments, they're windows into how fragile our web's existence might be, balanced on a razor's edge of physical constants. Take inflation theory, the leading explanation for the Big Bang's explosive growth. It suggests our universe is just one bubble in a frothing sea of spacetime, each bubble with its own unique laws. In some, matter might clump so aggressively that filaments collapse into black holes before galaxies can form. In others, particles could interact so weakly that no structures coalesce at all. The cosmic web we know, with its intricate balance of attraction and expansion, might be the rare exception, not the rule. And if that's true, it raises a haunting question. How many of these alternate webs are out there, woven from entirely different threads? String theory takes this further, proposing hidden dimensions where gravity leaks between universes, subtly altering how their webs evolve. Some models even suggest that collisions between neighboring universes could leave scars in their cosmic webs, anomalous voids or filaments that defy local physics. While we can't yet peer beyond our universe's horizon, these ideas challenge us to rethink the web's inevitability. What we call structure might just be a single variation in an endless symphony of possibilities. Yet the most profound implication isn't about other universes, it's about ours. If the cosmic web's existence hinges on precise, finely tuned constants, it hints that our universe's architecture isn't accidental. It's a masterpiece painted with a very specific brush, whether by chance, necessity, or some deeper principle we've yet to uncover. The web's fragility makes it all the more extraordinary. And as we unravel its mysteries, we're not just exploring space, we're testing the boundaries of reality itself, one filament at a time. Life in the cosmic web isn't just a question of where planets form, it's a puzzle of how the universe's largest structures shape the conditions for existence itself. Picture a galaxy like our Milky Way, nestled along one of the web's filaments like a traveler following a river through the wilderness. That filament isn't just a path, it's a lifeline, funneling gas into galactic hubs where stars ignite and planets coalesce. But not all rivers run the same. Some regions of the web are bustling metropolises, where galaxies cluster so tightly their collective gravity churns the surrounding gas into a frenzy. In these dense knots, cosmic radiation from quasars and supernova floods nearby systems, sterilizing planets before life can take hold. It's like trying to build a house next to a volcano. The energy is too fierce, the environment too harsh. Yet other regions might be too quiet. The voids between filaments, those vast cosmic deserts, offer little raw material for star formation. Planets here would orbit aging stars in near isolation, their skies nearly devoid of neighboring galaxies. Without the periodic influx of gas from the web's currents, these worlds might lack the heavy elements essential for life: carbon, oxygen, iron forged in stellar explosions and scattered by galactic collisions. Life in a void could be like a tree growing in barren soil, struggling to find the nutrients to thrive. So where does that leave us? Earth sits in what might be the cosmic web's Goldilocks zone, close enough to a filament to reap its benefits, but far enough from dense clusters to avoid their dangers. Our local group is a quiet suburb by galactic standards, with just enough interaction to keep star formation simmering without boiling over. But could life exist elsewhere in the web? The answer might lie in the web's architecture. Filaments act as cosmic conveyor belts, delivering not just gas but also the building blocks of life. Organic molecules hitchhiking on comets and asteroids could travel more easily along these highways, seeding planets across interconnected galaxies. The real wild card is time. The web isn't static, it evolves. Billions of years ago, filaments were richer in pristine hydrogen and helium, while today they're laced with heavier elements from generations of stars. A planet forming early in the web's history would have a different set of ingredients than one forming now. And in the far future, as dark energy stretches filaments thinner, the window for life might narrow, galaxies growing isolated, star formation slowing, the universe's vitality fading. What's striking is how much we still don't know. Could life huddle near black holes, drawing energy from their accretion disks? Might extremophiles thrive in the turbulent gas of filaments themselves, anchored to floating dust grains? The cosmic web doesn't just map where galaxies are, it charts the universe's potential for life in all its strange and wondrous forms. And as we search for answers, we're not just exploring space. We're tracing the fragile threads that might weave life into the cosmos itself. The cosmic web isn't just a scientific marvel, it's a muse. Artists across the globe have turned its invisible filaments into breathtaking visual symphonies, translating raw data into colors, textures, and forms that pulse with the universe's hidden rhythm. Take the work of data visualizer Kim Albrecht, whose digital renderings transform galaxy surveys into swirling rivers of light, each thread a highway of stars flowing through the darkness. Or the murals of artist Jose Francisco Salgado, where galaxies cluster like fireflies caught in a spider's silk, their glow illuminating the delicate balance of chaos and order. These creations do more than dazzle. They make the abstract tangible, giving form to forces that defy human scales of time and space. Virtual reality takes this immersion even further. Projects like Cosmic Web at the Hayden Planetarium let viewers step inside the universe's skeleton, floating past galaxies strung along filaments like pearls. As you reach out to touch a strand, it dissolves into a cloud of particles, an elegant reminder that this structure, while invisible, is as real as the air we breathe. These experiences aren't just artistic flights of fancy. They're grounded in supercomputer simulations, with every curve and knot reflecting millions of hours of astrophysical calculations. The result, a bridge between equations and emotion, where the cold precision of science meets the warmth of human wonder. Even traditional mediums find new life in the web's inspiration. Sculptures like Tomas Sarasno's Webs of Attent-S Ion weave nylon threads into intricate, suspended labyrinths, mirroring the universe's fractal beauty at a scale we can hold in our hands. Meanwhile, musicians like John Boswell aka Melodysheep compose symphonies using data sonification, assigning musical notes to galaxies based on their distance or velocity, transforming cosmic expansion into melodies that rise and fall like celestial tides. What's striking is how these artistic interpretations often anticipate scientific discoveries. Before telescopes confirmed the web's filamentary structure, painters like Van Gogh and Kandinsky created works bursting with swirling, interconnected forms, as if their intuition glimpsed truths later proven by math. Today, collaborations between artists and astrophysicists are yielding fresh insights. When illustrator Dana Berry worked with researchers to depict dark matter's distribution, her visualizations revealed subtle asymmetries in filament shapes that sparked new simulations. Art isn't just illustrating science here, it's guiding it. This synergy speaks to something deeper. The cosmic web's grandeur touches a primal chord, reminding us that creativity and curiosity spring from the same source. Whether through paint, code, or violin strings, these artistic explorations do more than educate. They awaken awe. And in a universe where the largest structures are invisible, sometimes it takes an artist's hand to show us the threads connecting us all. Standing beneath the night sky, we see pinpricks of light, isolated stars, distant galaxies, but the cosmic web reveals a deeper truth. We're not just observers of the universe. We're woven into its fabric. Every atom in our bodies was forged in stellar furnaces, carried along filaments of gas, and delivered to this tiny corner of the cosmos by gravity's patient hand. This realization dissolves the illusion of separation. The carbon in our DNA, the iron in our blood, even the calcium in our bones, these elements journeyed across the web for billions of years to become part of us. We're not merely in the universe, we are the universe, conscious stardust tracing its origins back to the first filaments that ever formed. This perspective forces a profound shift in how we view our place in existence. For centuries, humanity saw Earth as the center of creation, then our solar system, then our galaxy. Now we understand that even galaxies are mere specks clinging to threads in an immeasurable tapestry. Such knowledge could overwhelm, but it also connects us in ways earlier generations couldn't imagine. When astronauts speak of the overview effect, that transformative awe felt when seeing Earth from space, the cosmic web offers a grander version, the understanding that our planet, our species, and every civilization that ever existed are threads in the same cosmic embroidery. Wars, borders, and divisions shrink to irrelevance against this backdrop. The web doesn't care about human conflicts, it simply binds us all through shared origins and shared destiny. What does this mean for our future, for exploration? It suggests that venturing into space isn't about conquering the unknown, but about coming home, reconnecting with the larger story we've always been part of. When our probes map asteroids or our telescopes study exoplanets, we're not outsiders peering in. We're the universe examining itself, tracing the pathways that led to our existence. This shift could redefine space agencies' missions from planting flags to forging connections, studying how life might arise along other filaments, or how civilizations could communicate across the web's vast neural network. Perhaps most powerfully, the cosmic web offers a new lens for ethics. If we're truly linked to everything from the smallest microbe to the largest galaxy cluster, then harm to one thread risks unraveling others. Climate change, asteroid deflection, even the preservation of cosmic heritage sites on Mars take on new urgency. We're not just protecting Earth, but safeguarding a unique node in the universe's grand design. Some philosophers argue this view could inspire a cosmic stewardship, where advanced civilizations recognize their role as caretakers of the web's delicate balance. Yet humility tempers this vision. The web has existed for 13.8 billion years without us. It will persist long after we're gone. Our significance lies not in dominating the cosmos, but in comprehending it, in becoming the universe's way of understanding its own beauty. And as we continue to map the filaments that birthed us, we're not just studying the cosmos, we're learning what it means to be a fleeting, fragile, and infinitely precious part of something immeasurably vast. Public engagement transforms the cosmic web from an abstract marvel into something tangible, a shared discovery that belongs to everyone. Planetariums have long been gateways to the stars, but today's immersive shows go further, projecting the web's filaments across domed ceilings so audiences can float through its structure. Institutions like the American Museum of Natural History use cutting-edge data visualizations to wrap visitors in swirling galaxies and dark matter tendrils, turning complex astrophysics into an emotional experience. It's one thing to hear about filaments stretching millions of light years, it's another to feel dwarfed by them, to grasp their scale viscerally. These aren't just presentations, they're cosmic empathy machines, bridging the gap between equations on a chalkboard and the awe humming in your chest. Documentaries push this even further. Films like Cosmos, Possible Worlds, and The Fabric of the Universe employ cinematic storytelling to frame the web as a character in its own right, a dynamic, evolving entity with a backstory and future. By weaving interviews with scientists, animations of supercomputer simulations, and real telescope footage, they turn cosmic structure into a narrative as gripping as any drama. The best of these projects don't shy away from complexity. They embrace it, trusting audiences to follow along when ideas are presented with clarity and passion. A child watching might not grasp dark matter's quantum properties, but they'll remember the image of galaxies strung like pearls on invisible strings, and that spark of curiosity could ignite a lifetime of exploration. Then there's citizen science, where anyone with internet access can contribute to real research. Platforms like Galaxies invite the public to classify galaxies in telescope images, helping astronomers map the web's filaments. Over 2 million volunteers have participated, some uncovering rare objects professionals missed. Projects like Zooniverse's Radio Galaxy Zoo take it further, training participants to trace jets from supermassive black holes that might influence filament growth. This isn't busy work, it's collective problem-solving, where a retiree in Tokyo or a high schooler in Nairobi can advance our understanding of the universe. The cosmic web becomes a collaborative canvas painted by thousands of hands. The impact goes beyond data. When people engage directly with the cosmos, they internalize its lessons, the fragility of our pale blue dot, the interconnectedness of all matter, the audacity of human curiosity. Schools leveraging these tools report surges in students pursuing STEM fields, especially from underrepresented groups. A girl who labels galaxies today might design a space telescope tomorrow. A boy captivated by a planetarium show could grow up to simulate dark energy's push on filaments. By democratizing access, we're not just educating, we're cultivating stewards for the next era of discovery. Technology is erasing barriers faster than ever. Apps like Universe Sandbox let users simulate cosmic web formation on their phones, tweaking gravity's strength or dark energy's influence to see how filaments respond. Virtual reality experiences, once confined to labs, now run on consumer headsets, allowing users to stand at the intersection of galactic superhighways. Even social media plays a role, astronomers hosting live Q, and as on TikTok or Instagram break down jargon into bite-sized revelations, proving you don't need a PhD to ponder the universe's architecture. The beauty of this movement is its inclusivity. Whether through a telescope, a classroom app, or a VR headset, the cosmic web stops being an elite domain and becomes common heritage. It invites us all to be cartographers of the invisible, to share in the wonder of mapping what binds the cosmos together. And perhaps that's the most profound lesson. In a universe woven from connected threads, our greatest discoveries happen when we collaborate across disciplines, borders, and generations. The next breakthrough might not come from a lone genius in a lab, but from a million curious minds gazing upward together. For all we've uncovered about the cosmic web, its filaments still guard profound mysteries, each one a locked door waiting for science to find the right key. Take star formation. Logic suggests gas streaming along filaments should collapse easily into stars, yet something regulates this process with almost surgical precision. In some regions, like the Orion Cygnus arm of our Milky Way, filaments sparkle with newborn stars at a staggering rate. Elsewhere, similar structures remain eerily quiet, their gas reservoirs seemingly untapped. The difference might lie in cosmic turbulence, chaotic motions within filaments that prevent gravity from gaining traction until conditions are just right. Imagine blowing on a dandelion. Some seeds catch the wind instantly, while others cling stubbornly until the breeze strengthens. That delicate balance between motion and stillness could dictate where galaxies light up with stellar nurseries and where they remain dormant. Magnetic fields add another layer of intrigue. these invisible force lines woven through filaments like threads in a tapestry may act as cosmic sculptors. Observations from radio telescopes reveal fields strong enough to resist gravity's pull, channeling gas into narrow streams or propping up vast cavities within filaments. In the Musca molecular cloud, a filament so slender it would stretch from the Sun to Alpha Centauri if scaled down, magnetic fields appear to be the only thing preventing total collapse. Yet how these fields originate remains hotly debated. Are they remnants from the early universe, amplified over eons, or do they emerge from the churning dynamos of galaxies, bleeding outward into the web? The answer could rewrite our understanding of how structure evolves. Then there's the stubborn gap between theory and observation. Supercomputer simulations like Illustris TNG produce cosmic webs strikingly similar to ours until you zoom in. Real filaments often appear clumpier, their gas distributed in uneven knots that models struggle to replicate. Some astronomers point to overlooked physics, like tiny black holes seeding early density variations. Others suspect dark matter might interact with itself faintly, creating microclumps that ripple through the web's architecture. Even the humble neutrino, long considered too lightweight to matter, is now under scrutiny. Their combined gravity might subtly alter filament shapes in ways we're only beginning to measure. These puzzles aren't roadblocks, they're invitations. Every discrepancy between expectation and reality forces us to question assumptions, refine tools, and sometimes overhaul entire theories. When the Planck satellite's map of the cosmic microwave background didn't quite align with galaxy surveys, it sparked the sigma-8 tension, a statistical mismatch that still keeps cosmologists up at night. Could the solution lie in undiscovered particles, a flaw in how we model galaxy formation, or is the cosmic web itself feeding us clues about a deeper, hidden layer of physics? What's exhilarating is how much room remains for discovery. Upcoming telescopes like the Square Kilometre Array will trace magnetic fields across filaments with unprecedented clarity. Quantum sensors buried in Antarctic ice might catch dark matter's whisper, revealing how it sculpts the web's finest threads. Even artificial intelligence is joining the hunt, sifting through mountains of data for patterns no human eye could spot. The cosmic web isn't just a structure, it's a conversation, one where every observation prompts new questions and every answer reveals deeper mysteries. And in that endless exchange, science finds its purpose, not to declare final truths, but to keep unraveling the universe's grand, tangled story. The cosmic web isn't just a map of the universe, it's the story of how everything, from the tiniest atom to the grandest galaxy cluster, came to be. Picture it as the universe's circulatory system, with dark matter as its bones, gravity as its pulse, and filaments as the veins that carry the raw materials of creation. Every time we peer deeper into its structure, we're not just studying distant galaxies, we're tracing our own origins. The iron in our blood, the calcium in our bones, these elements were forged in ancient stars, then swept along the web's currents until they found their way into us. We are quite literally stardust woven into the cosmos' grand tapestry, but the web's significance goes beyond mere matter. It's a living record of cosmic history, etched with clues about how the universe evolved from a searing hot soup of particles into the intricate network we see today. The filaments whisper secrets about dark energy's relentless push, the peculiar behavior of neutrinos, even the possibility of hidden dimensions. Each discovery peels back another layer, revealing how delicate the balance truly is. Tweak gravity's strength by a fraction, or adjust dark matter's properties ever so slightly, and the entire web might have unraveled before galaxies could form. The fact that we exist to ponder it at all is a testament to the universe's astonishing precision. What's next in this cosmic detective story? The tools we're building today, like the Vera Rubin Observatories' all-seeing eye or the gravitational wave detectors listening for spacetime's faintest ripples, promise to reveal the web in ways we can't yet imagine. Perhaps we'll find evidence of exotic particles shaping filaments or uncover voids that defy our understanding of emptiness. Maybe we'll even stumble upon something entirely unexpected, a twist in the narrative that forces us to rewrite the rules. That's the thrill of science. Every answer births new questions, and the universe always keeps a few surprises up its sleeve. So the next time you gaze at the night sky, remember, those scattered stars aren't random. They're nodes in a vast, invisible lattice bound by forces older than time. And as we continue to chart this cosmic network, we're doing more than satisfying curiosity. We're learning what it means to belong to something infinitely larger than ourselves. The web connects not just galaxies, but all of us, threading every life, every world, every moment into a single, shimmering story. And that story is still